Hello, I invite you to watch an example of the second case of axial stretching and compression in a statically indeterminate system. A wooden beam is suspended on 3 bars. The first and third are made of steel. The second is copper with lengths L1, 3m, L2, 2m, and L3, 4m. Their cross-sectional areas are given by the relationship. A1 is equal to A2 and is equal to 2 times A3, and we have the Young's moduli given. The Young's modulus for the second material, for the second bar, is 105 GPa. For the first and third, that is, for the steel bars, is 210 GPa. The tensile strength of steel is 120 megapascals, and for copper it is 30 megapascals. Now we need to calculate what stresses arise in the bars. So to do this, we first need to measure these bars, because stress is the force in the bar divided by the cross-sectional area. To know the cross-sectional areas, we need to calculate the forces in the bars. Because we need to measure these cross-sectional areas based on the strength condition, and to do this, we need to have the forces in the bars. So we mentally cut the bars and mark the forces in the bars, N1, N2, and N3 here. And we have an external force of 75 kN. From static equilibrium conditions, we can calculate the sum of moments, for example at point C. Generally, we can make the sum of moments at any point and the sum of projections onto the y-axis. The sum of projections onto the x-axis is of no use here, because all forces act vertically. We have 2 effective equations of static equilibrium and 3 unknowns. Therefore, the task is statically indeterminate. I write down the sum of moments at point C. N1 rotates positively clockwise, that is, positively at an arm of 4 meters. N1 times 4 minus 75 counterclockwise at an arm of 2 meters, and minus N3 at an arm of 4 meters, equals 0. Here we have 2 unknowns in this equation. We need to leave one of them on one side and the rest on the right. And here we will have a relation that N1 is 150 plus 4 times N3 divided by 4. We can divide this by 4. We are left with 37.5 plus N3. So the sum of projections onto the y-axis equals 0. Here we have N1 upward, positive. Minus 75 plus N2 plus N3 equals 0. N1 is already dependent on N3. So now we can make N2 dependent on N3. And by rearranging, we get the information that N2 is equal to 37.5 minus 2 times N3. Here, in place of N1, I substitute 37.5 plus N3. In this part of the equation, I write 37.5 plus N3 instead of N1, and I make N2 dependent on N3. N2 is 37.5 minus 2 times N3. These 2 equations are not enough to solve this problem. We have 2 equations and 3 unknowns, N1, N2, and N3. We need to use the geometric condition here. So we have to consider how this beam will behave, how it will deform. The beam will not deform, but these 3 rods will deform. And how it will look after being loaded with this force of 75 kN. Yes, because it is applied from the left side here. Then definitely the left part of the beam will tilt more than the right part. So, in addition to the fact that all 3 rods will be stretched under the influence of this 75 kN force, it will also rotate in this way. Of course, approximately, but definitely in this direction. Well, because the force is applied from the left side, this displacement plan will look like this. So each rod will elongate, and in addition the beam will rotate. And here, by drawing a dashed line, we will create a triangle here. And using the theorem of Thales, or the similarity of triangles, we can write that this length, which I am showing here, to 8 meters, is like this length to 4 meters. Now how to express this length here? Because this entire vertical segment is the elongation of the first rod. Of course, this is all redrawn on a large scale, but to make it more visible. So this entire segment is the elongation of the first rod, which is delta L1. And here this cut dashed line, if you look at it, is delta L3. So this length that we want to take into the relationship will be the entire delta L1 minus delta L3. And here, analogously, will be delta L2. This entire length is delta L2. Minus delta L3, this will be what we want to take for the similarity of triangles. So in that case, delta L1 minus delta L3, which is this length to 8 meters, is like delta L2 minus delta L3 to 4 meters. So that is the geometric condition. We multiply both sides of the equation by 8. Here the denominator cancels, leaving us with 2 in the numerator. We distribute everything to the left side, and we have the third equation. This means we are now able to solve this system of 3 equations. 3 equations, 3 unknowns, it can be calculated. We know that delta L is the force in the rod times the length of the rod divided by Young's modulus times the cross-sectional area. So now instead of delta L1 we have N1 times 3 meters, E1A1. Instead of delta L3 we have the force in the third rod, the length of the third rod, E3A3. And here 2 times N2, the second rod is 2 meters long, Young's modulus for the second rod and the cross-sectional area of the second rod. We substitute this relationship we've previously determined for N1. We substitute this relationship we've previously determined for N2. And we also remember from the problem statement that the cross-sectional area of the first rod is the same as the cross-sectional area of the second, and it is equal to twice the cross-sectional area of the third rod. And we also had the Young's moduli provided. It's good to make a ratio of these moduli here because they are nicely given so we can easily compare them. It will be 1 to 2 because we have 105 GPa and 210. So the Young's modulus of the second material over the Young's modulus of the first is 105 over 210, GPa cancel out, and we get 1/2. If we multiply this skew, we will have that 2 times E2 equals E1. Now having this information, and what is underlined here, we substitute it into this equation. In place of N1, we put what was underlined at the top. Instead of E1, we write 2 times E2 because it's equivalent. And instead of A1, we write 2 times A3 because that is also equivalent, and so on. Here N3 remains 4 meters, and instead of E3, it is equal to E1, and E1 is 2 times E2. So instead of E3, we have 2 times E2. Area A3 remains, and here in this third term, we have, instead of E2, the relationship we determined earlier. Young's modulus E2 remains, and instead of A2 we write 2 times A3. And now if we multiply by E2 and A3, the entire denominator will cancel out. This is why we did all this, this is why we substituted so. And we will have the unknown N3, which we will calculate. So let's move this equation to the next slide. So as I said, we multiply by E2, A3, thus eliminating the denominator. Here we have 3 over 2 times 2, 3, 4 in front of the bracket in the numerator. Here we have 4 halves, which is 2. And here we have 2 times 2, 4 over 2, 2 in front of the bracket in the numerator. We multiply out the brackets, both brackets. We arrange it, leaving N3 on the left side and the rest on the right side. And we divide by what is next to the unknown. So we have the result N3 equals 6.94 kN. Now we substitute into the underlined equations from the previous slide. We know that N1 is 37.5 kN plus N3, so we have N1 equal to 44.44 kN, and N2 is 37.5 minus 2 times N3 from the previous slide, which is 23.62 kN. So we have all the internal forces in the rods. So we can move on to the strength condition and dimension these rods. The strength condition, that is, the stresses which are equal. Normal force in the rod, whether it is tensile or compressive divided by the previous cross-sectional area, must be less than or equal to. Here all forces came out positive, so all rods are in tension. So it must be less than or equal to the tensile strength. And we remember that we had a given relationship in the problem statement that A1 is equal to A2, which is equal to 2 times A3. Another possibility, another variant of this task, could be that we have to dimension each rod separately. That is, that we do not have such a relationship between the cross-sectional areas as here, but different forces come out in different rods, so there will be different stresses. And for these stresses, we would need to dimension each rod separately, so each would have a different diameter. That could also be a variant of the task. But here we actually have a given relationship, and we need to use that relationship. The cross-sectional area of the first rod must be the same as the cross-sectional area of the second rod, and half the smaller cross-sectional area must be for the third rod. Okay, we need to check each of the rods and dimension them so that the strength condition for each rod is satisfied. So the force in the first rod N1 is 44.44 kN, which is times 10 to the power of 3. And A1 is 2 times A3, so I substitute 2 times A3. It must be less than or equal to the tensile strength of steel, which is 120 megapascals, mega, which is times 10 to the power of 6. From this, I calculate by multiplying by A3 and dividing by 120 megapascals. I will have the result, A3, which must be greater than or equal to 1.85 times 10 to the power of minus 4 square meters. I substituted everything in base units, so the result is also in base units, which is square meters. And now we check the second rod. The second rod, I remind you, was copper, so here the force in the rod is 23.62 kN. A 2 is also 2 times A3, so it is 2 times A3. And it must be less than or equal to, but now we take the tensile strength of copper. From this condition, we have that A3 must be greater than or equal to 3.94 times 10 to the power of minus 4 square meters. Third condition, meaning the third rod. Well, here the smallest force is in it, and it is steel, so here we find that the area from the third condition, the result is 1 order of magnitude smaller. Because here, a thin rod would be enough to hold it, since the force in this rod will be the smallest. But we need to do it so that all 3 conditions are satisfied. So if you would draw all 3 areas A3 on the horizontal axis, this part of the conditions will be greater than or equal to when we take the area from the second condition, the largest area. So the cross-sectional area needs to be greater than or equal to 3.94, so we can take 4. Thus, we assume A3 is equal to 4 times 10 to the power of minus 4 square meters. So if A3 is that much, then A1 and A2 are equal to 2 times more, that is 8 times 10 to the power of minus 4 square meters. Now we are approaching the end of the task. Having measured the areas of the cross-sections, we can now calculate the stresses in all the bars specifically. So we move on to the next slide with this. So the stresses in the first bar are the force in the bar 44.44 kN, that is times 10 to the third, and divided by the measured area 2 times A3, that is 8 times 10 to the power of minus 4 square meters. And the result is 55.55 megapascals. So the data input into the calculator gives us the result in pascals, which has a lot of digits. To convert this to megapascals, you need to multiply by 10 to the power of minus 6. The stress in the second bar is 23.62, that is, the force in the second bar divided by the cross-sectional area is 29.53 megapascals. Note that the tensile strength of steel was 120 megapascals. And with this dimensioned area, we have not even half of that, but we dimensioned based on the second condition. So here in this second one, we are at the limit of strength. This condition was decisive, which is why we are here close to the limiting stresses, as there was 30 megapascals for copper. But here, calculating the stresses in the third bar, we see that all 3 hold up, right? The second one, because we dimensioned for it, is on the edge, but all 3 meet the strength conditions. So it's okay, here the lowest stresses are in this third bar, because the force is the smallest, and it is a steel bar with higher strength. But what would happen if we made a mistake in dimensioning here, and dimensioned not for this condition, but say for the condition of the first bar? That is, if we assumed, say, 1.9 for area A3. If we assumed area A3 as 1.9, then A1 and A2 would be 3.8. So let's check that. Thus, we dimensioned for the first condition, which is incorrect. But what would happen then? The stresses in the first bar would be here at the limit. 120 megapascals was the strength of steel. Because we are dimensioning from the first condition, we are here at the limit. So that 3.8 was the area. If we had assumed 1.9 for A3, then A1 and A2 would have been twice that, which is 3.8. We would be at the limit with the first bar, which is 120. But look what would happen to the second bar. If we divided 23.6 2 by 3.8, we would have tensile stresses of 62.16 megapascals with a strength of 30 megapascals. So the tensile strength limit is exceeded by more than twice. Well, then we could be sure that it wouldn't withstand that. Here the third bar would also withstand, the stresses being 36.53 megapascals. So here the stresses are also more than twice as high, but nothing is happening. Well, I won't even mention that if we dimensioned according to the third condition, the stresses would be about 120, if not more. So we need to interpret these results well. And well, I hope that with this example I have shown you that it is important to think carefully about which condition we are dimensioning for. As I mentioned earlier, there could be a different variant of the problem, and we could take each diameter, each area separately. That is, without any connection between the cross-sectional areas of the first, second, and third bar, we could dimension each one separately. And each would have a different cross-sectional area. But in the task description, we had these areas connected in this way, so we need to dimension as they instructed us. Well, that's it for this example. Thank you for your attention. I invite you to our Facebook page. I invite you to subscribe to the channel. Take care. Best regards. Goodbye.